Okay, kids, this next video that I'm going to set up for you is actually a collection of 4 videos that I pulled off the internet. This one called Effective Nuclear Charge from thechemistrysolution.com, one called On Ionization Energies. Those are both really good. They're pretty short. They have a great explanation in them. The third one is this nuclear charge and electron shielding video that another AP Chem teacher made for their students. It's a little bit longer. It's about 13 minutes, and I don't know that you need all of that, but it's pretty good. You could zip through it a little faster. And the fourth one is this kind of funny video. It's about 5 minutes of this kid explaining how he remembers electronegativity, atomic radius, ionization energy, and electron affinity. So if after watching the first 2 you think you want to skip the last ones, that's fine. You can stop it, fast forward it, whatever you'd like. But I thought I'd put them all together in one video because that would make things a little bit easier. So, okay, give it a look.
Hello and welcome to the Chemistry Solution. This tutorial is on effective nuclear charge. Although negatively charged electrons and atoms are attracted to the positively charged nucleus, they are at the same time repelled by other electrons in the atom. And so the effective nuclear charge is the average nuclear charge felt by an individual electron in an atom, taking into consideration the shielding effect of inner shell electrons. And we'll explore in more detail what that means as we go through this tutorial. The effective charge is equal to Z minus S, where Z is the number of protons in the nucleus, and S is the number of inner shell electrons. Now remember, the number of protons in the nucleus is the same as the atomic number and can be easily determined by using your periodic table. In this tutorial, we'll go through how to determine the number of inner shell electrons. Let's look at an example. What is the effective nuclear charge felt by an electron in the N equals 3 shell of sulfur? Remember that the effective charge is equal to the number of protons in the nucleus minus the number of inner shell electrons. The atomic number of sulfur is 16, and that means sulfur has 16 protons in the nucleus. Now let's start diagramming the electrons around the nucleus of sulfur. Remember that for a neutral atom, the number of electrons is equal to the number of protons. And so a neutral sulfur atom has 16 electrons. Remember that the N equals 1 shell of sulfur can hold 2 electrons. We now need to place 14 more electrons around the nucleus of sulfur. The N equals 2 shell can hold 8 electrons. So now we've diagrammed 10 electrons. The N equals 3 shell can hold 14 electrons total, but because sulfur only has 16 electrons and we've already diagrammed 10 of them, there will only be 6 electrons remaining to put into the N equals 3 shell. Now the question is asking us what the effective nuclear charge is felt by an electron in the N equals 3 shell. That means that both the N equals 2 and N equals 1 shells are inner shells. And so the number of inner shell electrons is equal to 10. This makes the effective charge for an electron in the N equals 3 shell of sulfur equal to 6. Now whenever you are looking for the effective nuclear charge felt by an electron in the outermost shell of an atom, and in sulfur the outermost shell is the N equals 3 shell, the effective charge will always be equal to the group number on the periodic table. But in some cases, you'll be asked to find the effective charge for an electron not in the outermost shell. So let's go through how we would do that. And we're going to use pretty much the same method. What is the effective nuclear charge felt by an electron in the N equals 2 shell of chlorine? A neutral chlorine atom has 17 protons and 17 electrons. For this example, I'm going to show you another way to diagram out the electrons so you don't have to draw an elaborate picture each time. Remember that the N equals 1 shell can hold 2 electrons. The N equals 2 shell can hold 8 electrons. So now we have 7 electrons left, 17 minus 8 minus 2. That means in the N equals 3 shell there will be 7 electrons, even though total the N equals 3 shell could hold 14. Now remember that Z is equal to the atomic number of chlorine, which is equal to the number of protons, which is 17. And S is the number of inner shell electrons. Remember that the inner shells are between the shell of interest and the nucleus of the atom, and in this case, because we're looking for the effective nuclear charge felt by an electron in the n equals 2 shell, the only inner shell electrons will be in the n equals 1 shell, and there are only 2 of them. This means that the effective nuclear charge felt by an electron in the n equals 2 shell of chlorine is equal to 15. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial. Hello and welcome to the chemistry solution. This tutorial is on ionization energies. The ionization energy is the energy required to remove an electron from an atom. The process of removing one electron from a neutral atom is the first ionization energy. You can also have successive ionization energies. The energy required to remove a second electron is the second ionization energy. And likewise, the energy required to remove a third electron is the third ionization energy. The greater the ionization energy, or the more positive the ionization energy, the harder it is to remove an electron. And the ionization energy increases with each successive electron removed. There is a sharp increase in ionization energies with the removal of an inner shell electron, or removing an electron from the noble gas core. And along with that, electrons in the outermost shells are the easiest to remove. Let's look at the periodic table trend for ionization energy. Ionization energies increase as you go from the bottom to the top of the periodic table. Remember that when you're removing an electron, you're removing it from the outermost shell. As you go down the periodic table, the size of the atoms becomes bigger, and the electrons reside in shells farther and farther away from the nucleus. And so the farther away an electron is from the nucleus, the easier it is to remove that electron. Ionization energy also increases as you move from left to right across the periodic table. Let's look at an example involving ionization energies. Arrange the following atoms in order of decreasing first ionization energy: francium, oxygen, calcium, and fluorine. And so we want to put these atoms in order from the one that's hardest to remove an electron from to the one that's the easiest to remove an electron from. First, let's locate these elements on the periodic table: francium, oxygen, calcium, and fluorine. Remembering our periodic trends that ionization energy increases as you go from the bottom to the top and increases as you go from left to right, that means that fluorine would have the highest ionization energy, followed by oxygen, followed by calcium, and francium would be the atom where an electron could be most easily removed. Between which successive ionization energies in an atom of aluminum will we see the greatest increase? So remember, the removal of the first electron is the first ionization energy. The removal of a second electron is the second ionization energy, and so on and so forth. And so we're looking for between which of those ionization energies will we see the greatest increase. Here I've drawn out the electron configuration for aluminum. The first ionization energy is the energy required to remove the 3p electron. Now I've drawn the electron configuration for my aluminum +1 ion. The second ionization energy will remove an electron from the 3s shell, and the removal of a third electron will remove an electron again from the 3s shell. So the electron configuration for the aluminum 3+ ion is 1s2, 2s2, 2p6. So you can see that now we've removed all of our outer shell electrons. And so between the third and fourth ionization energies is when we would see a sharp increase in ionization energy, because this requires the removal of an electron from an inner shell of aluminum. You might also remember that atoms tend to form ions with the same charge as their group number. So aluminum is in group 3 on your periodic table, and aluminum likes to form ions with a +3 charge. This gives it a stable noble gas configuration. So you'll always see a sharp increase in ionization energies between the ion that an atom is most likely to form and the removal of one more electron from that ion. So in the case of aluminum, aluminum forms ions with a charge of +3 because it's in group 3 on the periodic table. And so you'll see a sharp increase in ionization energy between the third and fourth ionization energies, or the removal of one more electron from that ion. It also might be helpful to draw out abbreviated electron configurations with noble gas cores, and then you can write out the electron configurations as you remove each successive electron. And you know that you'll see a sharp increase in ionization energies as soon as you have to remove an electron from that noble gas core. So if we look at this again on our periodic table, you'll see that the loss of one electron from aluminum results in the formation of an aluminum +1 ion, and that has the same electron configuration as magnesium. When we remove one more electron, we form aluminum +2 with the same electron configuration as sodium. And when we lose one more electron, we result in the formation of aluminum +3 with the same electron configuration as neon. And remember, according to the octet rule, atoms like to form ions with stable noble gas configurations and an octet of valence electrons. So once aluminum has the same electron configuration as neon, it's going to be very hard to remove one more electron from that atom. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.
Oh, you're back. Okay, welcome. So the objective in this video is to go a little bit deeper and to try to identify the underlying cause of periodic trends. So we've been talking about three properties mainly so far among the elements. One is atomic size, all right, how big the atoms are, and how the size of the atoms varies as you go across the periodic table or down the periodic table. Ionization energy and electronegativity. So these are the three main properties that we're focused on, and you just want to make sure that you're really familiar. By now you should know exactly what the trends are, both going left to right and up and down the table with respect to each of these three properties. Okay, now the trends that exist among these properties can be explained by variations in atomic structure. So you guys, you know about atomic structure, and specifically the two factors that we want to discuss right now are nuclear charge and the shielding effect. Okay, so I'll try to make that clear what each of these is about. All right. First, let's talk about nuclear charge. It's really very simple. It's the charge that resides in the nucleus, and what's the particle in the nucleus that carries electric charge? It's the proton, right? Some neutrons are neutral; they have no charge. So the positive charge that is concentrated in the nucleus is coming from the protons. And here you can probably see which element we're depicting. This is lithium, atomic number 3. So I've got 3 electrons out here. And I want you to notice something. So as we, again, hopefully I'd like you to have your periodic table out and ready to refer to as we go through this. So with your periodic table handy and you found lithium, now let's go across that second period, going left to right. So the next element would be beryllium. How do we make beryllium? Well, we have to add a proton, right? And so now we would have, that would give us 4 plus positive charge in the nucleus. And of course, to maintain charge neutrality, that is a net charge of 0, we got to have 4 electrons out here. Okay? And then as we continue going to the right, the next element would be boron. So that would be 5 protons in the nucleus. So now we have a charge of 5 plus. And the next one would be carbon, and and so on. So let me back up here. So back to lithium. Now I want you to pay particular attention to what's happening to the outer electrons as we add more protons in the nucleus. Okay, so here's lithium, there's beryllium, boron, carbon. Okay, so you can see, hopefully it was pretty obvious that the electron cloud is contracting as we increase the positive charge in the nucleus. All right, so to add a little text here, as we go, from left to right, increasing positive charge in the nucleus leads to stronger electrostatic attraction between the electrons and the protons, and that leads to contraction of the electron cloud. Okay, now up till now you might not have had, you've probably had more experience with magnets, like in real life, actually, handling real objects that are magnetic. And a good analogy is to think of this, think of the nucleus as, a magnet. Maybe this is like the North Pole, and it's pulling on the electrons, which might represent the South Pole of another magnet. And as you increase the charge, it's analogous to increasing the strength of the magnet. So the more positive charge that you pack into that small nucleus, the more strongly it's going to pull on the electrons, and that leads, as I say, to contraction. The radius of this atom is going to decrease, right? Okay, now let's connect that to the periodic table just to make sure. So in terms of atomic radius, here we are with lithium. That's what this shaded red area denotes. And as we go across the second period, you can see that the radius gets smaller and smaller. And if you were wondering up until now, like, hey, what's up with that? Why does the atomic radius get smaller as we go to the right? Geez, we're adding electrons. Shouldn't that make the atom bigger? You think so, but if you're really considering, the physics of the electrostatics that are going on between the nucleus and the electrons, actually, this contraction makes very good sense. Okay. Now, what about ionization energy? Why does the ionization energy get bigger as we go left to right? Well, again, as you increase the charge in the nucleus, the outer electrons are contracting a little bit. The distance between the electrons in the valence shell and the nucleus is getting smaller. And so, when that electrostatic attraction is getting stronger, you can easily imagine that it's going to get harder to pull those electrons away from the atom, right? And indeed, if you look at a table of ionization energies, you'll see that fluorine, which is what this represents, has one of the highest ionization energies. It takes a lot of work to get an electron away from a fluorine. Okay, so let's pause here. Not literally pause, but just kind of ponder for a moment. Hopefully, this makes it more clear why atomic radius gets smaller left to right, and why ionization energy gets bigger going left to right. Okay, so hopefully this is making a little bit more sense. Next, now we need to talk about electron shielding. So this is the second concept that we need to talk about. All right, so what I've got depicted here is an atom of helium, right? You've got 2 electrons, which I'm showing explicitly right now. I've got the little helium element highlighted. Now, what I've done is I've done away with the explicit electrons, and I'm just going to represent that those 1s electrons as a solid ring. Okay, so that's helium. Now, when we go to the next element, when we go back to lithium, you can see that there's this inner shell of electrons. There's 2 of them, and then this is the 2s electron. All right, so now this is the valence electron. When you read or talk about shielding, it's shielding in the sense that from the perspective of the valence electron, this electron is shielded from the nucleus by this inner shell. Okay, and so you can think of it as it's like the valence electron is being protected from the powerful electrostatic attraction of the nucleus. All right. Now I want you to notice something. As we march across the second period, I want you to look at what happens to the shielding. Okay, so there's boron. You've got 3 electrons. Okay, there's carbon, nitrogen, oxygen. There's fluorine, and there's neon. Okay, so my question for you, let me dial it back. What is happening to the shielding as we go left to right? Is it getting more and more, or is it decreasing, or is it staying the same? Well, the fact is, from the perspective of each of these valence electrons, as long as you're here somewhere in this second period, the shielding is the same. The shielding is coming from that inner, n equals 1 shell of electrons, and it's absolutely constant as you go left to right. What about in the third period? Okay, so this would be, do you know what element this is? That's right, it's sodium. So again, as we go left to right, you can see that the shielding is absolutely constant. It's not changing. In the third period, let me go back to sodium. In the third period, now there's 2 electron shells. And so there's more shielding. So elements in the third period are shielded to a greater extent from the nucleus than the elements in the second period. Okay, so it's like you've got an extra layer, like an onion, layers of an onion. So the further down you go in the periodic table, the more electron shells there will be between the nucleus and the valence shell. Okay, so this is to kind of summarize the shielding effect. Going left to right, the shielding is constant because when you do go left to right, you're simply adding electrons to the valence shell. You're not changing the number of inner shells. Now, what about top to bottom? Okay, so here's hydrogen. This is simple hydrogen, 1 electron. As we go down, there's lithium. So now we're going to go down group 1A. The shielding for lithium is coming from those 1s electrons, right? So there's 1 layer of electrons. Now, let's add another layer. Here's sodium. Sodium, the shielding that's available to it is coming from the first 2 energy levels, okay? And so those would be the 1s2, 2s2, 2p6 electrons. So there's a total of 10 electrons, standing between the nucleus and the outer shell electron. So I think hopefully it's pretty obvious that the shielding is increasing as we go from top to bottom, but it is constant when we are going left to right across a period. All right, so let's do a quick summary. All right, nuclear charge we saw earlier. Nuclear charge increases as we go left to right. What about top to bottom? Well, again, it increases because you're certainly adding protons in the nucleus as you go from top to bottom. Okay, shielding we just saw constant left to right. Shielding increases top to bottom. What about atomic size? Okay, this is just for a little recap. Going top to bottom, what does atomic size do? That's right, it increases. How about left to right? It decreases. And now we know why. You can actually explain why the atomic size decreases across a period in terms of nuclear charge and electron shielding. Ionization energy, as you go down, it decreases because there's more and more shielding. And so those valence electrons, which are the ones that are going to get removed when the atom is ionized, those valence electrons are protected by more and more shells of electrons as you go down a group. On the other hand, the ionization energy is increasing as we go left to right. Why does the ionization energy increase left to right? So hopefully you can answer this. Don't forget, within a period, the ionization energy is going to increase because the nuclear charge is increasing. Okay, so it's pulling harder and harder on those valence electrons. And finally, electronegativity. What's electronegativity doing from top to bottom? It's going down. Okay, just like ionization energy. And also like ionization energy, electronegativity is going to increase left to right. Okay, thank you very much, and we'll see you tomorrow.
I have a personal announcement, and that is that I hate periodic trends. But you have to know them probably, so I'm going to teach you. I'm going to teach you my little tricks for not having to actually do a whole lot of memorizing. Okay, when it comes to the periodic table, each of the different atoms has a different electronegativity. How are you going to predict, or how are you going to memorize where the highest electronegativity is and where the lowest electronegativity is and what the trend is? Here you go. Electronegativity. F has the highest electronegativity. So, the closer it is to F, the more electronegative it is. See? F is here in the top corner. I don't think my camera can focus when it's that close. F is up here in the top corner. If you're asked whether calcium over here or aluminum is more electronegative, the one closer to F is more electronegative. Piece of cake. You have to know what the numbers are. The same goes for atomic radius. When it comes to atomic radius, HE, which is kind of in the same corner as F, HE is the smallest. By extension, if HE is smallest, these are the biggest. And this one down here, francium or francium, FR, is actually the biggest. So, if you're asked which atom is bigger, and they ask you between, I don't know, calcium and aluminum, well, calcium is closer to the big area. Calcium is bigger. Piece of cake. Ionization energy can be trickier. Remember, ionization energy is the amount of energy it takes to remove an electron. Which atoms really want to give up electrons? These ones. It's not going to take a whole lot of energy for these to get ionized. Which atoms don't want to lose an electron? Well, definitely the noble gases, because they already have a full outer shell. And even the halogens, because if anything, they want to gain an electron to have that full outer shell. The last thing they want to do is give it up. So, what I would say there for ionization energy is that He has the largest ionization energy. That's going to give up, it takes a lot of energy to remove an electron from that. Doesn't take a whole lot to remove it from down here. So if you were asked about the ionization energies of, say, calcium and aluminum, calcium is going to give up its electron easier. It will have a lower ionization energy. And electron affinity is the amount of energy released when an electron is added to an atom. Which atoms are hungriest for electrons? The answer is halogens. Halogens would kill to have that extra electron. What I like to think is that F has the highest electron affinity. Boy, francium does not have an affinity for electrons. Now, there is one caveat to electron affinity. They classify it in with periodic trends. This electronegativity trend, really strong. Like if you looked at a table of electronegativities, it's a clear trend and it clearly increases as you get closer to fluorine. Atomic radius clearly gets smaller as you go this way. Ionization energy, there are a few exceptions, but in general, ionization energy increases as well. Electron affinity, this is pushing it. This isn't like... Electron affinities are kind of all over the place. But I guess, in general, you have higher ones in this area and lower ones in this area. Again, lots of exceptions. You'll have to suck that up. But this is how I like to remember what the periodic trends are. Electronegativity is highest here. He is small, like these are the smallest atoms. They have the highest ionization energy and the highest electron affinities. Good luck.